In this video, we're going to look at a quick recap of total internal reflection and then look at its application in optical fibres and look at how optical fibres are made, kind of constructed, work and used. So as a quick reminder, before we get into things, the way total internal reflection is normally investigated is you take a D block, and the actual block is made of glass with air outside of it. Now, what tends to happen is light is shone through the surface of the D block, and because at this point the light is travelling along the normal, it doesn't refract. Well, it changes speed, but it doesn't change direction because it's travelling along the normal. But when it gets to this point, it's going from a high refractive index to a low refractive index boundary, and what that means is it's going to bend away from the normal. So it will change direction like that. Now, really, I should be using a ruler for this, but just with the setup, it's quite difficult. So that is refraction at your high to low boundary. But what you've got is, if you have a normal here and we draw on the critical angle of this material there, what that critical angle means is that if the critical angle, which is the angle between the normal and this angle, if the angle of incidence from the incident ray is greater than that critical angle, you'll get total internal reflection. So at this point we have got refraction because we are not greater than the critical angle. What you might get is a partial reflection. So that is refraction. Partial reflection, but it's not total reflection. Now, if I draw a second diagram, giving myself a bit more space, here, if I draw the ray obviously greater than the critical angle, then we will get total internal reflection. So in this case, critical angle is about there, so we're greater than the critical angle, so the angle to the ray there is greater than the critical, means you've got TIR, total internal reflection. Okay. And a reminder, it must be greater than the critical angle, but you must also be at a high to low refractive index boundary. And if you can't remember what the refractive index is, it's a measure of how optically dense a material is. Air is about 1, and glass is higher than that. But what we're going to do now is just have a very quick look at another material before we get into the optical fibres, which is diamonds. So diamonds have an even greater refractive index than glass. And that's where this diagram comes in. What you can see is lights, what you can see is lights up at the top of this shot shining onto diamonds down further below. Well, if we zoom in, you can just about see it, but the diamonds are quite sort of sparkly. So you see this one here, you can see the light, and these ones here you can see kind of sparkles starting to come through. And just to show that even better, here's a video of it, and as the camera moves around you can see those kind of sparkles of the light. And if you look really carefully and pause it in the right place, you can see different colours. So here I can see a bit of purple, over here I can see some yellow, there's a little bit of green in there, carry on a bit and try and pause again. So particularly over here, just lots of different colours coming through. Now, the reason that happens is due to, it's due to total internal reflection, but it's also due to refraction and dispersion. So it's all of these properties of light changing direction happening. Okay, and I'll pause that somewhere where you can see. So, in terms of a diagram for this, diamonds are cut in a certain way to give them a certain shape, and as a rough version of that, this is the sort of shape they normally have. Slightly wonky, but there we go. So, in fact, we can do better. So the sort of shape diamonds normally have. Now, if you imagine red light coming in here. Now, red light, when it goes from a low to high boundary, refracts towards the normal. So it's coming in there, change direction, come in there. Now you can see that is a very steep angle. So it's gone from a low to high refractive index bent towards the normal. But when it hits this point, because it's now on a high to low boundary and it's a very steep angle, in fact in a diamond this is greater than the critical angle. So what happens is that light reflects off there, then reflects off again, and just as it hits the top there, and I'm just going to move the ray for demo purposes a little bit to this point. So what it is showing is the light total internal reflex hits this point, and at this point it's going to refract, and it's going to refract away from the normal, so it will do, that's a little bit straight. So at this point the normal is there, probably go off sort of in that direction. So what you can see is the light coming in, the light is coming out, not exactly in the same direction. Sort of ideally it would be very similar to the sort of opposite direction it came in, but you see it's, you know, it's refracted, reflected, come back out in a sort of similar to the way it came in. Now, sorry, opposite to the way it came in. Now, if you took blue light, it's traveling parallel, that is going to refract more than the red light. So you'll get a steeper angle there. That will reflect and reflect, and you can see it's then going to go away from the normal, so that will probably go more like that way. But you can see the two rays came in parallel, but due to the steeper angle of refraction there, it's coming out in a slightly different place. So because of these changing angles and the multiple reflections within the diamond, that's why when you see the sparkles, you can see different colours there, because the light is coming out in different places, which is quite cool. So that's a sort of introduction to how within a material you can have multiple total internal reflections. Now, a diamond is designed to have light come in, to come in, totally internally reflect a bit, and then come back out again, splitting up the light. Whereas what an optical fibre does, it is designed to keep the light in. So if I jump to a video here, it's a courtesy of Physics Demo's YouTube channel. If I have a little look at this,
the principle.
just pause that. What he's going to show, he's just picked up this plastic rod here, so I'm going to pick it up from the table, and what he's going to do is shine a laser through it. And what you can see here, you can see the laser light coming in, and it's reflecting, carry on down, it's going to come out this side. So this is sort of like how an optical fibre works. So it's this total internal reflection happening down here, but it's happening in the object. Now, in this case, this material isn't an overly pure form of glass, and what that means is you can see this light because imperfections in the glass is causing the laser light to reflect off, which is why the further the laser light gets down this, the more blurry and kind of less defined it gets, because the light is starting to scatter. So this is a demonstration of how light travels down a fibre, but isn't exactly how, because this isn't a total reflection. Quite a lot of the light is being absorbed here. Now what I'm going to do is remove that and that. We're going to start with this, and what I'm going to do is just show what a fibre is constructed of. Now, as he's got there, that is what we would call the core. And what the core is a piece of glass it's a piece of glass that light can travel through. What happens is you shine the laser light in, and as the laser light comes in, bends a little bit towards the normal, and it then reflects off the sides all the way to the end, and then it comes out the other side. Make sure that's all connected up. Now, if your core is always in air, then the boundary conditions are met in that this glass has a high refractive index and the air outside has a low refractive index. The problem is, if you then submerge that, or it gets wrapped in plastic, protective coating, anything else, then you no longer have your high to low refractive index. So what we do with fibres is we have the core that is made of a high density glass, and it's wrapped in what's called a cladding, which is also glass. So this is cladding and it's also glass, but the difference is that is low refractive index and the core has a high refractive index. Now what that means is you can then coat the cladding in a protective plastic coat and protective sleeves and whatever else you want to put on there, but you're not going to block the TIR from happening because you've got the cladding layer to ensure that the higher to low refractive index condition is always met. Okay, so remember there are two conditions to total internal reflection. It's greater than the critical angle, and the one people forget is that you must be on a high to low boundary. Okay, so that is how light travels down the fibre. Now, as a slightly better diagram, I've got this sheet here, and what we're going to do with that is fill it in. So let's have green light today. Now, you've got two examples of light rays coming into this. Just push this over a little bit. So two examples of light rays coming in. Now what I'm going to do is carry this one on. To the edge of the fibre. Now as light goes from a low to high refractive index, it bends towards the normal. Okay, Now, when you get to the cladding layer, remember the cladding is made of glass. This is just a demo, and what I'm going to tell you is at this point we are not greater than the critical angle. What that means is this light ray is not going to totally internally reflect, it's going to refract. And the way I can see it's going to do that, if I draw on a normal line, I need to bend on a high to low boundary away from the normal, which means my ray is going to go like that. Now when it hits this point, it ends, because what's normally outside the cladding is a protective coat, normally made of plastic, and it just absorbs the light ray. So that is the end of the ray. It's not going to get any further than that. So introducing our second light ray, which is at a better angle. Now at this point, this is going to bend towards the normal again. Oops. And at this point, the angle is greater than the critical angle. So you can see this is, see that angle isn't that steep. Whereas if they draw the normal here, we've got a much greater angle to the normal. So total internal reflection is going to happen here. And we need to make sure that the law of reflection is followed here, so that the incident angle is equal to the reflected angle. On the other side of the fibre, when it comes out, you've got the normal here again. Again, it's going to bend away from the normal, which is sort of like that. Okay. So that is a diagram showing light rays travelling through the fibre. Let's see if I can just focus on that a bit better. So have a go at that. Draw your own diagram to show light travelling through the fibre. Now, we're happy with the diagram. I just want to show you another bit of a video to show you this a bit more. Now, another demonstration you can do to show this, and this one's courtesy of the engineering guy. Just slightly lost my place in the video. Now, what he's got here is a bucket filled with, it's not water, it's some of the liquid, I'm going to call it water. But what he's going to do is take the bucket, fill it with that stuff, and what he's then got is a laser here. And what he's going to do is shine the laser through the bucket, and when he takes that plug out, the liquid comes out, and what you can see, it's a little bit dim, but the liquid is coming out of the bucket, and what you can see here is the laser light totally internally reflecting through the stream of the liquid. See if he gets a better shot here. There you go, that's a bit better. So the liquid is coming out here, and you can see this total internal reflection happening in the fibre. And that's the interesting thing with fibres, you can have the light travel round corners. As soon as you're greater than the critical angle, it will totally internally reflect all the way down. Okay. Now, the last little bit of video, courtesy of Learn Engineering, just shows how that works, a slightly better diagram. So there you can see the light ray totally internally reflecting down the fibre. And you can also see the light ray refracting towards the normal on the way in. And then they show a nice little version of it going around a bend there. Okay, so that is your light travelling down an optical fibre.